Hi, it's Mr. Beck. We are going to be talking about Hooke's law, which describes the force that a spring will deliver. And it is the last of the forces we need to include in our forces unit. So Hooke's law tells us Fs equals negative k times x. Fs is the force from the spring. It's the force that the spring responds with when you change the length of the spring. K is the spring constant of the spring. It's a measure of just how stiff or loose or stretchy a spring can be, and it is usually given in units of newtons per meter, but occasionally you'll see newtons per centimeter. And x is the displacement from equilibrium. So if you have a spring that is unstretched, then x is how much the spring is actually stretched from where it would be at rest. Now, if you take a spring and you compress it in, then the spring will be pushing with a force out. And if you take a spring and you stretch it, then it will reply with a force back towards equilibrium. So that's what the negative means in Hooke's law. That negative tells us that the spring will be replying in the opposite direction from which you are stretching it or compressing it. But since we're going to be drawing our forces with arrows, we usually know that we know which direction the spring force will be depending upon if it's stretched or compressed. So we typically will just write F equals kx, or sometimes F equals k delta x. But you have to know that it's how much the spring is stretched times the spring constant will give you the amount of force from the spring. So let's take a look at some problems. In this first problem, we have a graph of force on the y-axis versus x, which is the stretch of the spring on the x-axis. And it says the graph to the right describes the spring constant of 3 different springs. Which of the springs would be easiest to stretch? Now, we did a lab in class where we hung different masses on the spring, and we made a graph just like this, where as we increased the amount of force on the spring by hanging more masses on it, we saw that the spring stretched a greater amount. And so we were measuring the force of gravity on the mass, which was equal and opposite to the force that the spring was applying back up. In that lab, we hung a mass from a spring and we kept on increasing the amount of mass we had hanging, and so we could determine the force of gravity. A free body diagram at equilibrium would show that the force of gravity and the spring force were going to be equal and in opposite directions. So that was the lab we did in class. And what we found with different springs was that they had different slopes. And the slope here is going to be the force of the spring or the force of gravity divided by the distance that the spring is stretched. So it's rise over run. And in this case, the rise over the run is going to be the force of the spring or the force of gravity, which are going to be equal and opposite, as we said before, divided by how much the spring was stretched, which is our x. And that gives us our spring constant in newtons per meter. So the spring constant is the slope of each line. So if we want to determine which spring would be easiest to stretch, we could look at the one with the smallest spring constant, because that would take the least number of newtons per meter, so that would be the one with the smallest slope. We also could look at, for a certain stretch, just pick a random point, and look up at where we intersect each line. Spring C would require this much force to stretch that distance. Spring B would require this much force to stretch that distance. And spring A would require this much force to stretch that distance. So you can see that A requires much more force than C does, so C is going to be the easiest to stretch. This next problem tells us that a spring stretches by 0.15 meters when a force of 3.6 newtons is applied to it. So it stretches by 0.15 meters. So that's going to be the x that we're talking about, is how much the spring is stretched. 0.15 meters. And it says when a force of 3.6 newtons is applied to it, well, then the spring is going to respond with 3.6 newtons. So that's going to be the force in the spring is 3.6 newtons. Determine the spring constant of the spring. The spring constant is k, so that's what we're looking for, k. Now we have Hooke's law, which we can write as Fs equals kx, or we can rearrange that for k, the spring constant, is the force of the spring divided by how much it's stretched. So in this case, we're going to have 3.6 newtons as our numerator, and then x is going to be 0.15 meters. Plugging that into the calculator, you get an answer of 24, and the units are newtons in the top and meters in the bottom, so newtons per meter, which are good units for a spring constant. This next problem says a spring of length 18.2 centimeters. 18.2 centimeters. That's the length of the spring. That's not how much it's stretched. So we have to be careful with that. So I'm going to write that the original length of the spring, the unstretched length, L0, is 18.2 centimeters. Now, that's in centimeters, and if we read on, it says it's got a spring constant of 30 newtons per meter. So K is going to be 30 newtons per meter. Now notice we have centimeters and we have meters, so we really should convert centimeters into meters. So if we do the conversion, we multiply by 1 meter over 100 centimeters, we get 0.182 meters as the original length of the spring. It says what should be the total length of this spring? So the total length, that's going to be my final length of the spring. So I'm looking for L as opposed to L0. That's my question mark. If a 150 gram mass is suspended from it, well, let's draw a picture. This mass hanging from the spring is going to cause the spring to stretch. And if we assume that this is the stretched spring, then what we have is a free body diagram with the force of gravity on the mass pulling down and the force of the spring pulling back. And if those are in equilibrium and the spring's at rest, those two are going to be equal. So it's going to be very useful to figure out the force of gravity on this 150 gram mass. First, we should convert the mass that's in grams into kilograms because we want to get to newtons. So 150 grams times 1 kilogram over 1,000 grams gives me 0.150 kilograms. Now, to get the force of gravity, that's going to be the mass times the acceleration of gravity. So if we do Fg equals mg, that's 0.150 kilograms, and I'm going to use 10 for g, 10 meters per second squared. That gives me 1.50, and kilograms times meters per second squared is newtons. So that's the force of gravity. That's also going to be the magnitude of the spring force pulling back up. Now we can use Hooke's law, Fs equals Kx, in order to solve for x, the change in length of the spring. Substituting 1.50 newtons for the spring force and 30 newtons per meter for the spring constant, that gives us x equals 0.05 meters, which is also 5 centimeters. Now we're looking for the new length of the spring, and the new length of the spring is going to be the original length of the spring plus however much it's stretched. So I can write L is L0 plus x. So the original length was 0.182 meters. The change in length, or the stretch, is 0.05 meters, which gives us a new length of 0.232 meters, or 23.2 centimeters. So in this case, we could have taken the change in length, the stretch of the spring, and converted it directly to 5 centimeters and added that back to the original 18.2 centimeters. So as long as we're doing Fs equals Kx in newtons per meter and meters, then we will get the right answer. We can do our conversions later. In question 4, we're given a graph, just like we created in the lab, which is a graph of the force applied to a spring and the total length of the spring. So this isn't the change in length, this is the total length of the spring. And so first thing is we're determining the original length of the spring. And the original length is going to be the length of the spring when no force is being applied to it. So what we have to do is look here where the force is 0 and look on the graph to where it intercepts, because that is going to be the length of the spring when 0 newtons of force is on it. And so that's 0.1, that's 0.2, so that's going to be 0.14. So that's going to be 0.14, and the units are meters. So 0.14 meters would be the original length of the spring. For part B, to determine the spring constant, we know that the spring constant is the force of the spring divided by the stretch of the spring, not the total length of the spring. So sometimes we write this as delta x, But we already determined earlier that the spring constant is going to be the slope of this line, even if it doesn't start at 0. So what we need is the rise over the run for any portion of this line. So let's pick some points that make sense. Now the 2 points I picked were our original point there where the stretch is 0.14 because we've already determined that one, and that's with a force of 0. So if I make that x1, y1, I'm going to get 0.14 and 0. The second point I chose was the very top of the line. Sometimes it's easier to find the slope over a wide area. So if I go to the top of the line, then that point is at 0.50. It's right on the line. And then we go up to a value of 15, 16, 17, make that 18. And now the slope is going to be y2 minus y1 over x2 minus x1. So we get y2 of 18 minus y1 of 0, and x2 of 0.50 minus x1 of 0.14. In other words, it's the rise over the run, and I see that I'm going to go up this way 18, and then I'm going to go over this way is going to be the 0.50 minus the 0.14, or 0.36. So I have 18 divided by 0.36, which gives a value of 50, and the units of the 18 were the rise, which is newtons, so that's going to be 50 newtons, divided by the run, which is in meters, so it's newtons per meter. So that is going to be the spring constant of the spring, the slope of that line. This next problem says, in order to push an 800 kilogram boulder off to the side of the road, a worker uses a spring with a spring constant of 32,000 newtons per meter between her bumper and the boulder. If the coefficient of friction between the road and the boulder is 0.6, how much will the spring compress? Well, that sounds kind of complicated, so let's start off by drawing a free body diagram of the boulder. Now, if we take a look at the boulder, the spring is going to be pushing the boulder to the right. So we do have the bulldozer pushing the spring, but then the spring pushes the boulder. So that's going to be a force of a spring to the right. We, of course, have a gravitational force straight down towards the center of the Earth. We have a normal force that's going to be from the Earth pushing back on the boulder, and that's normal. And then in the backwards direction to the left, parallel to the surface, we're going to have a force of friction. So initially, we're going to be pushing, and we're going to assume that it's going to be moving. We're going to assume it's moving at a constant velocity. And at a constant velocity, we know that the force of the spring, the rightward force, is going to equal the force of friction, the leftward force, because we'll be in equilibrium as we move at a constant velocity to the right. We also know that gravity and the normal force are going to be equal and opposite in this case, because the forces in the up direction are going to be equal in magnitude to the forces in the downwards direction. So up equals down, left equals right, moving at a constant velocity. So which of these do we know the values of? First, the force of gravity is going to be the mass of the boulder times the acceleration of gravity. And again, I'm using 10. So that's 800 kilograms times 10 meters per second squared, giving me 8,000 kilogram meters per second squared, or 8,000 newtons. So that's the force of gravity. But since we determined that the upward force and the downward force are going to be equal, here I have the normal force up. So that's also going to equal the normal force. The force of friction is going to be the coefficient of friction times the normal force, and we're given that the coefficient of friction is 0.6. So 0.6 times 8,000 newtons gives me 4,800 newtons, 4,800 newtons as the force of friction. And since the force of friction, since I'm moving at a constant velocity to the right, that friction is going to equal the spring force, so I can write that equals Fs. Now the force of the spring is going to be equal to the spring constant times the amount that the spring is stretched, and we're looking for x. So we can rewrite Hooke's law, Fs equals kx, to be x equals the force that the spring is applying divided by the spring constant. And this is going to be the magnitude of the force. Remember, I got rid of the negative in Hooke's law just to talk about magnitudes of forces. So the amount the spring is going to be stretched or compressed, in this case compressed, is going to be the force of the spring divided by the spring constant. Plugging in the 4,800 newtons for the spring force that we got before, and the 32,000 newtons per meter for the spring constant that was given up in the problem, we get a value of 0.15, and of course newtons divided by the quantity newtons per meter is going to give us meters. So 0.15 meters is how much that spring is compressed. And our final set of problems deal with this picture up here, where we have a block on a table being pulled by a spring, and then there's some applied force being applied to the spring itself. It says a 12 kilogram block, so let me just write 12 kilograms on that block, is being pulled along the table at a constant velocity. This is the sort of thing that you look for. That's kind of magic words. Constant velocity tells me that forces are balanced. So up equals down, left equals right. By a spring held horizontal to the table. If it was not horizontal, then we'd have to do some trigonometry and kill the monsters, as I say. The spring has a spring constant of 105 newtons per meter, so that's K equals 105 newtons per meter. The spring constant is stretched by 0.25 meters. That's the change in length of the spring, so that's what we call X is 0.25 meters from its relaxed length. So it's stretched from its relaxed length. That's the change in length of the spring as the block is pulled. It's asking for the coefficient of kinetic friction between the block and the table. So let's take a look at the free body diagram of this block. What I have to the right is not the applied force, but actually the spring force, because the spring is what's touching the block. We have a force of gravity straight down towards the center of the Earth. We have a normal force perpendicular to the surface, in this case straight up, and we have a force of friction to the left. In this case, since we're moving at a constant velocity, we know that all the forces are balanced and the object is in equilibrium. So the force of normal is going to equal the force of gravity, and the force of friction is going to equal the spring force. Now we're given K and X, so what we can solve for immediately is the force of the spring is going to be K times X. So that's going to be my 105 newtons per meter times my 0.25 meters. And that will give a value of 26.25 newtons. So that's going to be the force of the spring is 26.25 newtons. And that's also going to be the force of friction because the force to the left has to equal the force to the right. So this is also going to be 26.25 newtons. Now, we know that if we're looking for the coefficient of kinetic friction, we know that the coefficient of friction is going to be the force of friction divided by the normal force. And we know the force of friction in this case is 26.25 newtons. So now we just need the normal force. And if it's 12 kilograms, we know that the force of gravity is m times g is going to be 12 times 10, giving me 120 newtons. And so in this case, since we're at equilibrium, the normal force and the gravitational force have to equal, so the normal force is also going to be 120 newtons. So I can write for the normal force 120 newtons. And that gives an answer of 0.21875, which we can round to two significant digits and get a coefficient of friction of 0.22 in this case. And remember, the coefficient of friction is unitless because we have newtons on the top and newtons on the bottom, so therefore the units newtons cancel, and we just get a coefficient of 0.22. Now the last problem here, problem number 7, says for the problem above, the block hits a patch of oil on the table where the friction drops to 0. What's the acceleration of the block if the force from the spring remains the same? So in this case, everything's the same except what we're doing is we're getting rid of the force of friction here. So let me just take my eraser and erase the force of friction from this free body diagram. Now what we can see is that we still have a normal force and a force of gravity that are equal and opposite and canceling, but we've got a spring force to the right that is unbalanced external force, and that force is going to accelerate the mass. So in this case, the net force on this block is going to be, the spring force is going to be that 26.25 newtons. So that's the net force on the block, and the mass of the block is 12 kilograms. So the acceleration of the block is going to be, from Newton's second law, the net force divided by the mass. So we're going to have 26.25 newtons on the top, and we're going to have 12 kilograms on the bottom, and newtons divided by kilograms is going to give me meters per second squared, and that gives an acceleration of 2.1875 or 2.2 meters per second squared. So that's going to be the acceleration of the block, and it's going to be directed, of course, to the right. I hope that was a little bit helpful, and we'll see you again here sometime soon. Bye.